I'd like to thank Tiago and Professor Gustavo also for inviting me. Okay, let me, before starting, make a little comment about the reason why the flag is standing there. I think the only way we have as academics to at least express our discontent with the atrocities which are happening in Gaza is to at least say a few words. And it's simply inadmissible what's happening, and we should say something. We should at least put a flag in your talks. And let me tell you a personal story to show you the power that this group has, not just inside Israel, but throughout the world. I have been a member of the IEEE Fellow Committee, Evaluating Committee, for several years. And recently they added a person from Israel. And I said, well, I don't want to participate in a Zoom meeting with people from that country. So I would participate, but I want to do it via email. So you send me the CVs and I will evaluate. And this is a person I know for many years. He didn't reply to me, and he simply removed my name. So I'm not a member of the fellow committee because I dare to question the validity or the honesty of the people who are going to be sitting there. So just a personal story. Yeah? Anyway, so this is, I try to promote a book that we wrote 3-4 years ago, together with my former students. These 3 guys are former PhD students with me. And the book is this one, PID Passivity-based control. I can send you the way where you can buy it, the Amazon link. And we're trying to promote the book. The idea of the book, I have been working on PIDs, like everyone else, for 30 years or so. And recently, we managed to formalize the use of the property of passivity. So we want to design PIDs in a different way than the standard way, in the sense of being able to ensure stability. So we want to design PIDs such that you know for sure it's going to be stable for all choices of the gains, of the KP, KI, KD. So that's the main message. We're going to show you how to do that. Design a PID where you can play with the gains and you know that it's always going to be stable for whatever choice you make of KP, KI, KD. So that's the main message. There is this folk aphorism. I read it in a paper by Carl Ostrom. He said that PIDs are universal controllers because they capture the present in the proportional action, the past in the integral action, and the future in the derivative action. I think this is a very nice aphorism, and it really captures why PIDs are so popular, and they're popular because they work. They usually work. And they work, but the problem is that you have to have a good tuning. So the main problem is to tune the PIDs. So you know that 90 or 92% of all industrial applications in the world are PIDs. So that's, you can see, it's really a complete domination of this kind of controllers. So this is the layout. This is a little bit long. I will try to skip some of the topics. Particularly the last topic is PIDs of mechanical systems. It's really, I don't know how far interested are you in mechanical systems. It's a little bit beyond the remaining theory. So you have to do some particular things to deal with PIDs of PVCs. But the rest I will try to cover in. So just some preliminaries and then PID-PBCs. I believe that you're familiar with most of the preliminaries which are there, passivity theory, equilibrium, and so on, and then go to the main topic, PID-PBCs. Okay? So some preliminaries. The numbers in there correspond to references at the end. So I will leave the slides here in case you want to check the references. Okay? So first, the definition of passivity. So there are many ways of defining passivity. The one I like the most is this one. A casual dynamical system, it does not even need to have a state. It's just a map from U to Y. It's said to be passive or passive if this inequality holds true. So the product UY, and then you have a minus sign in there, is smaller or equal to beta. So the logic behind that, or the physical interpretation, is if u and y are conjugate variables in the sense that the product is power. So for instance, voltage and current, torque and velocity, and so on. The product of voltage and current is power. The integral of power is energy. So what this inequality is saying is that the energy that you can extract from a passive system is finite. So this is the minus sign, is meaning the power is flowing from the system to the environment. So passive systems are universal. So there are no physical systems from which you can extract an infinite amount of energy. Okay? Now there is a reinforcement of this concept. It's something called output strict passivity. So there's an epsilon positive standing in front, and input strictly passive, there's a u and a delta standing in front. Okay? So as indicated in the last bullet, u times y is power in physical systems, and as I said before, simply says that you can, sorry to repeat it again, but it's an important message. The amount of energy that you can extract from a passive system is finite, and it's the energy that you had at the beginning. So either you have some initial conditions, or you have some battery that will run out. So you can extract only the energy that was at the beginning. Okay? So this is the more general definition without the notion of state. It turns out that we are interested in physical systems, and physical systems satisfy physical laws, and physical laws can be expressed in terms of state space laws. So you have a state, so the state will be fluxes, charges, velocities, positions, and so on. So if you have a state and you have a representation like this, then the definition is a little bit sharper, in the sense that there should exist a function h, which is called the storage function, such that this inequality holds true. So if you remove the h, which is a positive function, the non-negative function, then you fall into the previous inequality, because hx0 is positive, and you just remove the hxt. But this is the definition that we're going to use in order to be able to prove stability. So we want to prove stability, so we need state space representation. We can prove stability with input-output theory, only without state space representation, but then the kind of stability is input-output stability, so L2 stability, L infinity stability, and you want to prove things like Lyapunov stability, for instance. So you need a state space, okay? That's why we consider, throughout the talk and throughout the book, we consider state space systems all the time, even though you could do a theory only for input-output representations. And again, input strictly passive, output strictly passive, okay? This is a very important theorem. The interest of the theorem is theoretical. It's not a practical. It's a translation of the passivity property into a set of algebraic equations. So a passive system, the system is passive if and only if you can find two functions, L and W, such that these nonlinear algebraic equations hold. Okay? In the linear case, this is the famous Kalman-Yakubovich-Popov lemma, the positive real lemma. So this is the nonlinear version of the Kalman-Yakubovich-Popov lemma, which I believe you're familiar with. So instead of nabla HF, you have the PA plus A transpose P in negative definite, PB equals C, a condition which is the positive lemma. Okay? So as I said, the interest of this is basically for comprehension and understanding, because solving these nonlinear algebraic equations is, of course, very difficult. Okay? You need to find the H, and you need to find the L and the W. But there's one thing that is going to be very important in our talk, is the concept of, let me see I forgot the word. I'm drinking too much cachaça. The dissipation obstacle. Sorry, the dissipation obstacle. We're going to prove that there is an obstacle that we call dissipation obstacle that hampers the possibility of designing PIDs. So for some systems, you have to do a modification of the output in order to be able to apply the PID with stability guarantees. And this is seen if you look here, this condition has to be satisfied. So if the system, remember we're talking about systems of this form, so if the system is relative degree 1 or more, this J is 0. Okay? So if the J is 0, you come here, this term here, W is 0, and if W is 0, this is 0. So if that is the case, there is just one passive output. Okay? And that unique passive output is G transpose nabla H. So I repeat again, for systems of relative degree larger than 0, so 1 and more, there is just one passive output, which is G transpose nabla H. If not, then you can play with the J, you make a relative degree 0 plant, and you generate W and so on and so forth, which is the game we're going to play. But keep in mind that if you have relative degree 0, then you larger than 0, sorry, there's just one passive output, okay, which is, it's called the natural passive output, this one here, okay, which is this remark here. If J equal to 0, and we're going to call it YHM in honor of Hill and Moylan. This is a theorem from the late 70s. It's a very old result, the PhD thesis of David Hill. Okay. Now, what is the passivity theorem? This is our main tool for stability analysis. So you have a feedback interconnection, classical feedback interconnection. You assume that the feedback interconnection is well posed. Well posed simply means that if the inputs belong to a certain space, usually L2, is square integrable, then all the signals inside belong to the extended space. Okay, so this is well posedness, and people think that this is really a theoretical condition, but it's not. It's very easy to design systems where you put interconnection is not well posed. It can very easily cook up examples where this is the case. But let's assume it's well posed. Okay? If it's well posed, then we have the following proposition, which is, I think, is the most general version of passivity theorem, which is in the book of Vidyasagar, by the way. So let's assume that each one of these systems, sigma 1 and sigma 2, satisfies an inequality like this, with epsilon 1, epsilon 2, delta 1, delta 2, non-sign definite, so some real numbers. Okay? If epsilon 1 plus delta 2 is larger than 0, and epsilon 2 plus delta 1 is larger than 0, then you have L2 stability. Okay? So the interpretation of this is that one of the systems, if this guy is negative, means that it's generating energy. If it's positive, means that it's dissipating energy. So what this inequality tells you is that the energy that is generated by one of them is dissipated by the other. And that ensures stability. Okay? So that's why you can allow these epsilons to be negative as long as the corresponding delta is larger than the negative part. So this is, the interpretation is, as I said before, the lack of passivity is compensated by the excess of passivity that you can interpret in terms of energy generation. So energy, if it's not passive, it's generating energy. And if it generates energy, the feedback part should dissipate more. Okay, so that's the interpretation of the passivity theorem. By the way, you can interrupt me anytime you want. If you have any question, go ahead and please shoot. Okay? Okay, this is the main property of the whole work, that the PIDs are passive. Okay? So a classical PID is actually more than passive, is input strictly passive. So this is the equation of a PID, the input to the PID and the output of the PID, integral, proportional, integral, and derivative term. Okay? View it as a map from UC to YC, which is the input-output map of the PID. It is input strictly passive. So it satisfies this inequality. So there's a U here. Kp is positive. You choose Kp to be positive, Ki to be positive. Kd may be 0, because there are systems which are relative degree larger than 0, then you cannot put a derivative term. And then the lambda mean is here, and there exists a beta which is real. So this is the definition of input strictly passive system. And the proof is a triviality. Just make the product UC YC. YC, you take it from here, is equal to this identity. This is positive definite, larger than lambda mean Kp. And these two guys, they cancel if you replace xe dot here, okay? And at the end of the day, then you integrate this guy and you get the property. This is the beta, and what I have here, the lambda mean Kp appears here. So the proof is really 2 lines, that the system, the PID, a classical PID, is input strictly passive. And the important thing, and this is true for any value of Kp, Ki, and Kd that satisfies these inequalities, okay? And that's what we're gonna use. So we're gonna take the PID, find or construct an output of the system which is passive, and then use it as input here. So the UC is going to be the output of your system that you're going to select this output to be passive. That's the idea. And if you have that, you know that because of stability, because of the passivity theorem, you have L2 stability, and with some additional conditions, you have convergence of the states. Okay? Is that clear? This is the main point. Okay. Okay. So this is the main result. You have now a PID here, a plant, and you assume that the plant, if U to Y is passive, so from here to here is passive, this Y is input strictly stable, then the overall system is L2 stable. So if D is square integrable, Y will be square integrable. And with some additional assumption, which is called detectability, detectability is a generalization of observability for nonlinear systems. So under an additional assumption that is easy to check, well, relatively easy to check, you also have Y tending to 0, okay? So this is the main configuration. We're gonna either find an output of the plant or construct an output of the plant such that the map from U to Y is passive and put it in closure with the PID. Now, the question that you may ask, well, the output that I want to control is not necessarily passive output. So what do I do? Okay, for instance, if I do control of a motor, I want to feedback the current, or a power converter, you want to feedback the voltage, and it's not a passive output. But the point is that under these assumptions, you have not just that the Y goes to 0, we're going to prove later on, you also have that the state will go to the desired value or to 0. Okay, you have something more than just input-out passivity, input-out stability, sorry. So this is the main objective, wrap the PID around the passive output. That's what we're going to do. And then you will have to be able to construct outputs for your given plant, which is passive or strictly passive. Okay? There are some preliminaries on equilibrium assignment because we're going to be interested in stabilizing equilibria. We want to try to prove something more than just input-output stability. We would like to prove Lyapunov stability. So the end of the talk is, how do I prove Lyapunov stability from that property? Okay? I need to construct a Lyapunov function. Okay? And we're going to do that. Okay? And we'll talk about this so-called dissipation obstacle. Actually, we took the term, it's sometimes called pervasive dissipation. This is used in civil engineering. In civil engineering, when they are studying vibration of buildings, in words, the dissipation obstacle is that you still keep dissipating energy even after the equilibrium is reached. So the equilibrium, the state equilibrium is reached, but there's still dissipation going on. And that's why this phenomenon is called the dissipation obstacle. So there are buildings that even after the earthquake is finished, they keep oscillating, for some finite time, of course. But then this property in civil engineering is called pervasive dissipation, okay? Okay, so in terms of mathematics, we have the following. So this is just notation. If I give you a mapping from Rn to some matrix, I'm going to put the map, and I give you a fixed value x star. I'm going to call S star. Oh, sorry, this should be S, sorry, here. This should be S, okay? It's the evaluation of the map at the point. And there's a typo here, sorry. Now, this is very well known. If you want to find the equilibria of this system, so you want to solve this equation, you multiply by this matrix, which is a full rank matrix, where G perp is a full rank left annihilator of G, so satisfies this with this rank condition. and you take the transpose here, multiply. So you multiply this by full rank matrix. So the solutions of these equations are the same as the solutions of these equations. And from here, you get this expression. So this set, the set of x star such that g perp star f star is equal to 0, is the set of assignable equilibria. Okay? And there is a unique value of u star which will assign the equilibrium, which is this one here, where this g spade is the pseudo inverse of the matrix. Okay, so this equivalence is going to be used all the time. Okay, to be able to identify first, on one hand, the set of assignable equilibria. So think, for instance, of a system with b equals 0, 1. So the first row, x1 dot, has to be 0 because there's no control. So the first row of x dot has to be equal to 0, and this is precisely this equation. Okay. So it's a generalization for nonlinear systems of a well-known result. So this is the set of assignable equilibria and the univocally defined corresponding control. Okay, just a preliminary. Okay, now, if you have passive systems which j equal to 0, you will have the dissipation obstacle. Let me explain what do we mean by dissipation obstacle. So you have a system like this, but j is equal to 0. So relative degree larger than 0. So from Hill-Moylan properties, we take the second equation, and it's equal to this because j is equal to 0, the j term disappears, so you only have here. And hx, as I said before, is the only passive output. There's just one passive output, which is this guy. Now let's go to the power balance equation. So the differentiate of S, as the energy of the system, is nabla S times this, and this has to be equal to this. Okay? But this plus this is the power balance equation. The stored energy or power is equal to the dissipated energy plus the supplied energy. So at an equilibrium, x star, this guy has to be equal to 0 because this term is equal to 0 at an equilibrium. So at an equilibrium is equal to 0. This means that L star transpose L star transpose equal to 0. This means that y star u star equal to 0. So at an equilibrium, the power that you supply to the system has to be 0. Okay? But it turns out that there are physical systems where this is not the case. I'm going to present some examples in a minute. But interestingly, in mechanical systems, it's always the case. Okay? So dissipation obstacle does not appear in mechanical systems. That's why it took us a long time to understand it, because we started our work in robotics with mechanical systems, and there we didn't see the dissipation obstacle. But when we moved to motors, electromechanical systems, and so on, we observed the dissipation obstacle. So there were some problems in the proofs, and it's because of the dissipation obstacle. Okay? So the definition is the following. A system does not suffer from the dissipation obstacle if the power at the equilibrium is equal to 0. What does it mean? It means that I can't stabilize the plant just providing finite power. Okay? Remember, from a power system, from a passive system, I can only extract the finite amount of energy. So if the system requires an infinite amount of energy to be stabilized, it cannot be stabilized by a passive system. So in particular, it cannot be stabilized by a PID. Okay? So actually, this result is even more strict, not just for PIDs. Any controller with an integral action, any controller, any nonlinear controller with an integral action will have this condition. Okay? If it is not true, if it suffers from the dissipation obstacle, then we call this pervasive dissipation. So what did I do? Sorry, I'm moving in the wrong direction. Oops. It's only moving in one direction. Okay, sorry, here. Okay? Okay, so that's a definition of pervasive dissipation, or the definition of the dissipation obstacle. Okay? Now, let me show you these two examples, okay? These very simple examples. This circuit, okay? You stabilize an equilibrium, any equilibrium, eventually the voltage flowing through here is going to be 0. So there's not going to be current flowing through here at the equilibrium, okay? But this here, any equilibrium, any voltage different from 0, there's going to be current flowing from here. So this has pervasive dissipation. So even at the equilibrium, there's dissipation of energy in this resistance. While here, the voltages compensate, and at any equilibrium, the current stops flowing. So this system at the equilibrium does not dissipate energy. While this one, at any equilibrium different from 0, so the only equilibrium where it does not dissipate energy is when this guy is 0, the voltage 0, then there is always a flow of energy. So stabilizing this system requires to extract an infinite amount of energy from the source. Okay? While this one here, you can stabilize with a finite amount of energy. That's the essence of pervasive dissipation. Okay? A dissipation that's still present even at the equilibrium. Now, in mechanical systems, why in mechanical systems you don't have this problem? If you're interested in regulation, so driving the position Q to some value, then the output, the associated output is the velocity, so velocity is 0 at the equilibrium. So in mechanical systems, you don't have pervasive dissipation, okay? Because the product of force times velocity is 0, because velocity at the equilibrium is 0, okay? So that's the difference, okay? Now this proposition is very important. So you consider a passive system FGH in closed loop with the PID controller. A necessary condition for X star to belong to the equilibrium set, to be an assignable equilibrium, is that the system does not suffer from the dissipation obstacle. So if this system FGH suffers from the dissipation obstacle, you cannot assign that equilibrium, okay? So you not even stabilize it, you cannot even assign it, okay? And the problem actually is more general than that. This is true for any nonlinear dynamic controller that has an integral action. So if you integrate y, this phenomenon is going to appear. You will not assign, not even stabilize, assign an equilibrium. So making an equilibrium of the closed loop, if there is dissipation obstacle. Okay. So that's going to be for us one of the problems to overcome. How do we create outputs that do not have the dissipation obstacle? And that, if you go back to the slide, the previous slide, that means that you have to consider outputs of relative degree 0. Because if you have outputs of relative degree 1, with the j equal to 0, with the L equal to 0, then you have the dissipation obstacle. So we're going to create outputs which are relative degree 0, okay? Are the only ones that will allow us to control with the PID, because the PID has an integral action on y, okay? Now, it turns out that for this class of systems, port-Hamiltonian systems, the analysis simplifies and you can get stronger results in the PID-PBC. Okay? So what are port-Hamiltonian systems? Are systems described by this equation. J is called the interconnection matrix, is skew symmetric. R is called the dissipation matrix or damping matrix, is semi-definite, positive semi-definite. This guy contains Kirchhoff's laws. So in the J matrix will be a matrix of zeros and ones, which is just codifying the Kirchhoff's voltage law and Kirchhoff's current law. And the U times Y is power. So in electrical systems, voltage, current, mechanical systems, speed, force, and so on, okay? And then this system is very easy to verify that satisfies this power balance equation, because J is skew symmetric. So when you evaluate H dot, you get nabla H transpose J nabla H equal to 0, and you want to recover this part. So this is, again, the power balance equation. The stored energy is equal to the supplied minus the dissipated energy. And this, we can write it in terms of power or in terms of energy, integrating this equation, okay? Now, an interesting property is the invariance of pH structure. So if you design, if your plant, you describe it in this form, and you design a controller, let's say, which is also admits a port-Hamiltonian description, then interconnection will still be port-Hamiltonian. So it's the structure is invariant, okay? And this has a nice geometric interpretation, which is interpreted in terms of something which is called a Dirac structure, but I'm not going to enter into that. So you can go to infinite dimensional versions of this and so on, okay? Okay. Any question on this point here? Okay. Okay, so let's talk about PID and PID-PBC. Okay. So as I said, the PID controllers overwhelmingly dominate engineering practice. And if you look into questionnaires or investigations people have made with practitioners, they're happy with PIDs, but the only problem is how to tune them. They want them to find a way to tune them properly. Because before, I mean, 50, 40 years ago, the system operated in one point. You have a washing machine that operates only in one point. Now the washing machine operates in 10 different versions with different temperatures, different velocities, and so on. So the operating point is going to change. So if the operating point is going to change, the linearization is going to change. So you need to do some retuning of the gains depending on the operation point. So you have things like gain scheduling, for instance, auto-tuning, adaptation, to be able to track this variation of the parameters. But it turns out that if you have a PID that auto-tunes, so the KP, KI, and KD will readjust, then the users are going to be, in general, happy. So they're happy with the PID if it's properly tuned. Okay? Now, this is the main motivation. The PIDs are input strictly passive. Hence, if the plant is passive, you will have closed-loop stability. So what is the main advantage of this? Is that the tuning, it's a selection of KP, KI, KD, it trivializes a little bit exaggerated. It's not trivialized, but at least you know that you can select any positive value. Otherwise, the user has to be changing KP and KI and KD, remaining positive and not ensuring stability. There are going to be some values of KP, KI, and KD positive, which destabilize the plant. But if you do it for a PID-PBC, you know that you will not destabilize the plant. Any KP, KI positive, KD positive semi-definite is going to work in the sense of stability, not performance. And then you just have to tune among the set of positive gains. So that's the main advantage of PID-PBC. Okay? Now, there are a series of key issues. Well, the first one is how to identify passive outputs. I need to find a passive output, which is not necessarily the output that I want to drive to zero. Okay, I want to drive, for instance, some current or some speed to zero is not necessarily passive output. Okay, so I have to identify another output such that if I drive that output to zero, your desired output will go to zero or to some value. Okay. Now another question is, how about if the output reference value is not zero? In many cases, for instance, speed control, you want to drive the speed not to zero, but to some other constant value. Okay. And this is a fact that if the system from U to Y is passive, that does not mean that the system from U to Y minus Y star is passive, except in linear systems. In nonlinear systems, this implication is not true in general. Okay? So you cannot, if you find an output which is passive and you use it with the error, with Y minus Y star, then you don't have any guarantees of stability because it's not passive anymore. Okay? Another question is, how about if I go beyond just regulation, now tracking? So Y star a function of time. And the third question, or the fifth question, is if I go beyond just driving Y to Y star, if I go to have a stronger stability property like Lyapunov stability of an equilibrium. So what can I do? Okay? So these are the questions that we're going to ask throughout the talk. Okay? So this is the standard PID-PBC for output regulation to zero. This was reported 25 years ago or something like that, in the PhD thesis of a student in France. Okay? So this is the basic PID-PBC. Okay? You consider a system F, G, H, J, which is passive, in closed loop with the PI. In this case, because you have a J, you cannot use the derivative term. Okay? So you can use the derivative term only if you have relative degree larger than zero. Okay? And then this is the well-posedness condition that I mentioned before, which is generically true. Okay? Now you can prove that the map from this external input to Y is L2 stable, so you satisfy this condition. Now, if additionally, there's no additional input, B equal to zero, and H, this H, which defines the passivity of the plant, is proper, then you have Y going to zero. So in this particular case, the detectability condition that I mentioned is satisfied with just properness of H. So H being a proper function, then guarantees that Y goes to 0. Okay. Now, if you have now the possibility to add a D, so now you have a relative degree 0 plant here. You add a D term, well, you still have the same result. Okay. Now you can add a D term, which is this one here, and you still have the same kind of result. Okay. But this can be done only for relative degree larger than 0 plant. If the plant has relative degree 0, you cannot add the derivative term. Okay? Now this is a result on trajectory tracking, but for a class of bilinear systems. The interest of this class is that it contains the large majority of power converters models. So the buck converter, boost, the choke, all these converters belong to this class. And this result, actually, the first time we reported this was in the context of power converters. It has about 500 sites. And interestingly, of these sites, many of the sites are from the power electronics community. So the people from power electronics, they understood this, and they understood it. Why? Because it's closely related. Actually, it's a generalization of a well-known result in power systems, which is the PQ controller of Akagi, a Japanese author. So that controller is widely used in the power electronics community, the Akagi PQ controller. Well, it turns out that this one, I actually talked with Akagi in Tokyo Institute of Technology, and he agreed. They said, okay, this generalizes our result. You have more degrees of freedom, but then people can understand it. So it's very important if you want to have an impact on applications community to make it understandable for them. And the easiest way is to relate with the things they do. So for instance, field-oriented control in motors or director control and so on. You can explain it, the variations you do in terms of what they do. And then it's very easy, or easier at least, to penetrate the community so that they use your work and they cite you. Okay? So this is the case of this result. Actually, this is, as I said, the generalization of Akagi's PQ controller. Okay? So the class of systems is this one. We're adding a D because in the first time we reported this work was a temperature control problem. And in that case, in semiconductors, so they have the measurement of this external signal. But okay, it's just assume that it's a known signal. And then you have assignable trajectories. You said, I want this state to track these trajectories, okay, for some U. You define the error system, and then you find this is the error equation, okay? Now, you need some assumption on the B matrix and the A matrix. So the A matrix has to be stable, so it had to satisfy the Lyapunov equation, and the B matrix had to satisfy this coupling, okay? So it's a particular class of bilinear systems where the P that allows you to prove stability of the A matrix is such that you satisfy this condition. This is a non-generic condition, of course, but it turns out that it is verified by the power converters, okay? And the control objective is to find a U, assuming D known and P known, such that X tilde goes to 0, okay? And the main result is, I'm going to use a PID. The main result is to find a passive output. So I construct this output. I'm calling it YT, the T stands for tracking. So this matrix is a time-varying matrix that depends on the reference trajectory. So I construct this matrix, which is, as I said before, is a time-varying matrix. I construct this YT multiplying, well, this in the single output cases will be a vector, okay? Construct this output and define U tilde as U minus UR, where UR is the output the input that will ensure that your trajectory is followed. Then you can prove that the operator from U tilde to YT is passive, okay? So we constructed an output such that the mapping that we're interested in, which is U tilde to YT, is passive. Consequently, I can control it with a PID, So once I construct this output, I can just apply a PID, and I know that I will follow the reference trajectory. Okay? So this is a quite general result. And this is the proposition. You now apply a PID around this output, and you can prove, actually, more than yt going to 0, you can prove that this goes to 0. And under some rank conditions, you can prove global state tracking. So X will follow XR, the reference, okay? So that's, as I said, was reported in a context of a semiconductor problem, temperature control. But for power converters, it has been really very, very successful. And we have, like, I think 100 papers on this, on application to different topologies, in different scenarios, and so on and so forth. Multi-level control converters and so on. Okay? These are two former students. So now for power converters, it takes this form. So these are the switches. The user, remember, in power converters are switches that takes value in between 0 and 1. If you do the average model and so on, is the average of the switch 0, 1, is the duty cycle. The J matrix are skew symmetric and so on. And then you construct this output. This is the output of the previous case for the problem of regulation, not tracking, regulation. I want to drive X to some X star. So the output, it becomes now this thing, what I had before, okay, this new output. And I apply a passive system, and then you can be sure that X tilde goes to 0. Okay? So this is a controller. This is applying a PI to an output that you construct outside. Now, the criticism to this construction, of course, you need to know the E, the G, the Qs, and so on, but you also need to know the X star, okay? But usually you know where you want to drive your state to X star, okay? So this is, if you look at this from the point of view of the PQ Akagi controller, it's a generalization of the PQ. They call it instantaneous power, or instantaneous reactive power is called, okay? Which dominates the applications in inverters, okay? Now, as I said, we have applied this result. This was the PhD thesis of the previous student about 15 years ago. And in that period, we have done a lot of applications for different topologies. And also for this very interesting case, the constant power load, which is a case that appeared recently, appeared in the last 15, 20 years, 10, 15 years. Usually you model the power converters feeding a dissipation, so a resistor or some passive load. But it turns out that the new application of converters is to connect alternative generation units, so windmills or fuel cells or solar cells, to the grid, okay? You connect to the grid. And to connect to the grid, you need to translate from DC, which is the energy generated by this alternative energy, to AC, so you need an inverter. And the scenario now is such that what these converters are looking at is not a passive output, it's not a simple resistor. Because the grid and the final user has also some power converters installed in their computers, their TVs, and so on, that they know that in order for these devices to operate properly, they have to have constant power, okay? So these converters which are installed in these devices are ensuring that the device, the equipment inside the device looks at the constant power. So now the converter that you have designed to connect your alternative generation units to the grid is looking at constant power. So constant power, can I write here? I'm sorry, there's no. Is there a pen here? Oh, and probably here.
I think we don't have Romeo.
Here. Yeah. You see, the difference is really fundamental. So if you look at BI, okay, of the load. So you have a converter feeding some load here, okay? This is the load. This is the power converter, okay? So we usually take the load to be simply a resistor or possibly a nonlinear resistor, okay? But now when you have constant power load, BI is equal to a constant power. So the plot now is something like this. So what the converter is looking is at this nonlinearity, okay? And that completely changes the scenario. So if you want to control a power converter that is feeding a constant power load, you are confronting a radically different mathematical problem because you're looking at a hyperbola here instead of a straight line or a first-order quadrant, okay? So that was a very challenging. There were, I think, 4 or 5 students working on this in different configurations for different converters. For instance, for multi-level converters, that was very challenging to do that. Okay. Okay, this is some of the papers which I refer at the end. And in many cases, we have experimental results. So this was work done with practitioners, with people from power electronics community in France, and in a company also did some work for Schneider Electric and so on. Okay, let me talk about an application which is quite recent. This is with some Mexican guys. It's a PhD student, Carlos Beltran. Diego and Rafael are my former PhD students, and they are in another town in Mexico. And they had a problem of voltage regulation of a fuel cell-based power system. So they have the equipment, and the scenario is the following. You have a fuel cell standing here, and then you have a power converter that is feeding, in this case, is a passive load, a constant load. So the control objective is to design an adaptive, easy-to-tune PID-PBC for the output voltage regulation, even though the load changes, because the load is gonna be a motor. Okay, it's not a resistor, it's a motor, and the motor will operate at different speeds. So we assimilate this by a resistance which is time varying. So what do you need to do? This model does not, you don't know RP or RL, because this one is changing, this is not known. This is a mathematical characterization of the internal resistor of the converter, okay? And the difficult part is that what is called the polarization curve of the fuel cell is this nonlinear expression. So the relationship between voltage and current here is characterized by this nonlinear expression. This is very well known in fuel cells. If you look at Pokrushpan thesis and all the papers that have been written for characterization of fuel cells, you will find this nonlinear function, okay? But it turns out that it's monotonic. So we're gonna use the monotonicity of this map to design our control. So if you write the state space system, you get something like this with the nonlinearity here, which is the map, this map here. And you want to design a controller that will regulate the voltage in here, okay? So the first thing that you need to do is to estimate RP and RL, okay? And this is done with immersion and invariance estimators, okay? I'm not gonna enter into the details. This is just a design to estimate constant parameters. So this estimates the RP and the RL, okay? So we implemented this. And you know that you get global convergence of the parameter estimates. This is, as I said, from the immersion and invariance theory. This is a different book that sometimes I will come again and teach about the immersion and invariance. And this is the adaptive PID-PBC. So this is just a PID-PBC where you use this output, which turns out to be passive. So this is one particular case of the general passive output that I described before for that particular topology of the converter. It turns out to be just this expression, okay? And these guys are, it turns out that these guys, they have to be the solutions of the estimated equilibrium equation. So you have this equation and you have your estimates online, and you have to solve this for x1 star, okay? And then you can prove, you cannot prove asymptotic stability but you prove practical stability. So you converge to a residual set that you can, around your desired equilibrium, and you can make the size of the set as small as possible, increasing the gains. So that's called practical stability. This is a very complicated problem. We cannot prove global convergence, but at least you enter a ball in the residual set that you can make as small as you want. Okay, well, this is just a scheme. In this kind of journals, they ask you to provide these kind of things. They like these designs. And well, these are just some, let me skip the results. There's experimental results where you change the speed of the motor that corresponds to changing the resistor. Actually, we tried both, when they are actually resistors or when it's a motor. And then try to track the variation of the load, which is the variation of the resistors. Okay? This is experimental results. And then regulation of the state x1 and x2 to the desired values, x1 star, x2 star. Okay, so it worked very well. And this is the parameter estimation. When you change the load, you see you track the parameter changes, okay? And then if you change the references, as I said, you change the references, the value that you are using to represent the load is a resistor, it also changes. So you have to be able to track it. Okay. Sorry, I'm running out of time. Yeah. Can I over 15 minutes more? Yeah.
Can you explain again the practically stability? I'm not familiar with the term practically stability.
Well, a closed-loop system is practically stable. You're given an equilibrium that you want to stabilize asymptotically. But you cannot prove asymptotic stability. But you prove that you enter a ball around this equilibrium, and you can make it like ultimate stability, something. No, it's global. You converge from... No, but you can start whatever you want, but you will enter a ball. You will not necessarily go to the X star, but you can define a ball. So I can give you a radius of the ball, and I can make that, practically means that you can make the ball as small as you want by increasing the gains. But the problem, if you increase the gains, then you have an amplification of noise, and you don't want to do that. Okay? Like in sliding mode. Sorry, I have to say it. Okay. I'm sorry, I'm really running out of time. Let me skip some of these things. Okay, the first question is, what about if the reference value is non-zero? This is to drive y to 0. If it's non-zero, then you need to prove stability from the incremental input to the incremental output, or at least from the input to the incremental. And this is called shifted passivity. Okay? So now you have a different property, not from u to y, but from u to y tilde, or y tilde y minus y star. Now, in general, it's very difficult, but you can do it for generalized pH, for pH systems. Okay? And let me just show you, okay, this one here. Okay, I think this is an important result. You're given a port-Hamiltonian system, and you want to characterize all passive outputs. Hill-Moylan is not a characterization. It is passive if and only if you can solve these algebraic equations. But a characterization is, I give you some degrees of freedom, which are going to be 2 functions. So any function that you plug in is going to create a new passive output. I think this is a fundamental result. It was reported in a transactions paper. And it's the following. You're given a port-Hamiltonian system, and the following statements are equivalent. The mapping is passive, or the mapping, remember, H and J are y equal hx plus jx, okay? H and jx can be expressed as this for some mappings. So you plug in, you put any W here, you put any D here with skew symmetric, it's going to create a new output, okay? So it's going to define a new H and a J, which you know is passive. So this is truly a complete characterization of all passive outputs. You choose any W, you choose any D, you plug it in here, and you find you constructed a passive output. And that's what we're going to use to construct passive outputs. So this inequality will hold true. Okay? Okay, let me let me present this result. Sorry, I really too many slides. I think this is a result we're very proud of. It's an if and only if condition for shifted passivity. Shifted passivity, remember, is from U to Y tilde. So Y tilde is Y minus Y star, okay? So the proposition is the following. You're given a port-Hamiltonian system with the following things. G and R, the G is the matrix here, and R is constant. And then you say that the system satisfies this, which is the definition of shifted passivity, if and only if this inequality holds true. Okay? So you go and check, you have your J, your R, your Q, and so on. You check this inequality, and if it's smaller or equal to 0, then you know that the system is shifted passive. Okay? So this is, I think, the strongest result available for shifted passivity, but with the constraints that G and R are constant. We have been struggling a lot trying to stand this, but it's very difficult. So to get an if and only if, we need these two assumptions. Okay? Okay. 10 minutes?
Sure.
Okay. Okay, so let me talk about now the Lyapunov stabilization. Okay? So I know how to drive x to x star, but I would like to prove that x star is a stable equilibrium in the sense of Lyapunov. Okay? So what I need is a Lyapunov function. Okay? But to construct this Lyapunov function, it turns out, I'll come back in a minute to this preliminary material. You have this situation. Let's talk about port-Hamiltonian systems and the PID. Okay? And you know that this function, you add the energy of the system. This is the term that you need to prove passivity of the PI, and you know that U dot is smaller or equal to 0. But the problem with this function is that it is not positive definite. So it does not qualify as a Lyapunov function. You know that it's a function of the state, the full state, the state of the plant, the state of the controller, whose derivative is negative semi-definite, but it's not positive definite, okay? Because this guy is not in X star, okay? So what do? Well, you are going to do something that is used in inversion and invariance and in several techniques. You're going to create a manifold, which is an invariant manifold, such that you can drive the trajectory towards the invariant manifold, and in this manifold, this function is positive definite. This is called an immersion. Okay? So we need a little bit of preliminaries. So you say that the set, well, let's talk about the manifold already. So a manifold is a set characterized by an algebraic equation, basically. So the set of roots of this mapping is called a manifold. And then the theorem says that this manifold is invariant. So invariant means I start in the manifold, I remain in the manifold all the time, if and only if gamma dot is equal to 0. Okay? But it turns out that we are interested not in gamma dot equal to 0, but any level set of this graph, which is called a foliation. It doesn't matter to me if it converges here or converges to the second one, because once inside, I know that this relationship is true, which is what I want. Okay? So I'm going to create a foliation which is invariant. And the foliation is invariant if and only if gamma dot is equal to 0. Okay? The manifold is invariant if and only if the manifold is invariant if it is only if it's 0. The foliation is invariant if and only if this equation is equal to 0. Okay? So I'm going to create an invariant foliation. What is the idea? The idea, if I go back here, to create a Lyapunov function out of these separable functions, this depends on x, this depends on xc, is to create a dependence between xc and x, and create a new function such that the new function that I created, where xc is replaced by a function of x, is positive definite. So I'm going to create a gamma c equal, xc equal gamma x, which is an invariant set and globally attractive, such that I will move inside, and once inside, this becomes a function only of x, because xc is a function of x. This is the idea, okay? This is the idea used in inversion and invariance and in several observer theories, okay? So we have to create this, this set. Sorry. And, well, unfortunately, to create invariant sets, you need to solve partial differential equations. So you need to evaluate, to solve this differential. You don't know, you're looking for a gamma such that this partial differential equation is solved, where you have the h, the g, the phi, the w. But the interesting thing is that from the previous result of characterization of all passive outputs, I know that I can inject any w and any d. So this is a parameterized PDE where I can play with these guys, okay? So I need to find a w and a d such that this equation holds for some gamma. And once I find the gamma, then I know that I can replace the xc by gamma plus some constant, which is the level of the foliation. And this constant, I know it because it depends on the initial conditions. And now I have my Lyapunov function. My Lyapunov function is a function only of x, is the evaluation of the previous function for xc equal to gamma plus kappa. And then my PID will be, this is the PID, but evaluated only for x, okay? Because this is xc on the manifold, okay? So that's the way to construct the Lyapunov functions. I'm sorry, I know I overstretched.
No, you're fine, Romeo. You can.
Okay. Well, then of course the question is when can I solve this PDE? And it turns out that there are several cases depending on whether f is a gradient vector field. There are several particular cases where we get explicit solutions of the partial differential equation. Okay, let me skip that. And what we use to solve these partial differential equations is the so-called Poincaré lemma. Okay? The Poincaré lemma says the following. I give you a vector field beta from Rn to Rn. And I want to know under which conditions this vector field is a gradient vector field. So a gradient vector field is a vector field which is the gradient of a scalar function. So gamma is a scalar function, beta is a vector field. So you know that there exists a gamma such that this is true if and only if this condition holds true. This is so-called Poincaré lemma. And it turns out that this, again, is a partial differential equation. You have to solve this guy. But then when you have a gradient vector field, you can do simpler things, that if you have an arbitrary vector field. So that's the idea. So we can compute gamma by integration. Okay, okay, sorry, I'm going too fast. Well, this is an example. Let me see, how do I wrap up this? Okay, let me finish with example, okay? So this is a micro-electromechanical optical switch. When I started engineering, this was called the model of a microphone. This is actually the model of a microphone. But now it's used in the literature of micro machines. So for instance, this is a way to model surfaces like in expensive cars that you sit and then it latches to your back. So there are 1 million of these guys inside the car, and when you push into the back of the seat, it will close to you. You probably have driven a nice BMW or Rolls Royce or something like that. They have these kind of things. This was posed to me by Professor, not Bhattacharya, an Indian professor from Texas A&M. And the problem is the following. This is the model, very simple model, okay, where h of x is a Hamiltonian system. H of x contains kinetic energy, potential energy. Notice that there's a fourth power, and the electrical energy, which is the model of the capacitor. This is basically a capacitor. Okay, so x3 is the charge. Okay, and then you have charge, position, and velocity as state. So you have this system, And you want, the problem is that you cannot measure velocity. Okay? You can measure only position. And you want to position these two plaques at the value Q star without the measurement of velocity. That's the problem, okay, given this dynamical system, okay? And let's assume that you measure all the state except velocities, okay? So it turns out that you can control it with the PI, okay? This is designable equilibrium sets. You know that this is, you can stabilize, and you can solve the PDE, and this is the solution of the PID-PBC, you see? This guy is going to be the passive output. You create this passive output, okay? And then you have x3 minus x3 star, and you can prove that with this PI, this is a PI controller, you ensure global asymptotic stability of x star, and you can construct the Lyapunov. I'm sorry, I think I overstretched, but thank you very much.
There you go.